Modern theoretical physics is trapped in a contradiction. On macroscopic scales, general relativity models gravity as the smooth, continuous curving of spacetime. On microscopic scales, quantum mechanics insists that reality is composed of discrete, probabilistic states. While Einstein's field equations map macroscopic gravitational phenomena with incredible accuracy, they inevitably collapse into mathematical errors when attempting to describe regions of extreme density. When models break down at the center of a black hole or the primordial Big Bang, it indicates a loss of predictivity. This failure implies that differential invariance cannot hold at the microscopic or ultraviolet limit. Differential invariance is the core principle of relativity, stating that physical laws must remain the same regardless of the coordinate system used to map them. If the math fails at the smallest scales, we are forced to conclude that the four-dimensional spacetime manifold and the metric tensor used to measure it are not fundamental constituents of reality. They are effective, coarse-grained descriptions of something much deeper. The variable slice density, or VSD, framework synthesizes the eternalist block universe, the concept that the past, present, and future all coexist simultaneously, with the branching multiplicity of quantum mechanics. Traditional physics models gravity as a dynamic force, and relativity as an interaction mediated across time. The VSD model entirely discards this assumption. Apparent forces are actually time-independent, structural gradients within a static four-dimensional geometry. Observers do not feel the pull of a force. They simply experience a varying density of structural space as they thread their way through it. To construct a functional theory of quantum gravity, we have to abandon the assumption of a smooth manifold and mathematically prove how the gravitational metric emerges hydrodynamically from a discrete, quantized substrate. At the extreme ultraviolet limit, the VSD model defines the universe as a discrete collection of structural building blocks called configuration vertices, existing within a relativistic Hilbert space. A relativistic Hilbert space is a mathematical vector framework that organizes quantum states while respecting the absolute speed limits of special relativity. Each of these individual vertices represents a distinct classical 3D geometry, complete with its specific material and energy content. To translate this static 3D geometry into the four-dimensional progression we perceive as time, physicists use the ADM 3+1 decomposition. The ADM decomposition is a formal mathematical method that slices a four-dimensional spacetime metric into three spatial dimensions layered over a single parameter of time. This formulation separates the spacetime metric into a shift vector and a lapse function. The lapse function is critical. It dictates the rate at which proper experiential time flows relative to the universal coordinate time. The core mathematical relationship of VSD phase 2 dictates that the ADM lapse function is inversely proportional to the slice density of these configuration vertices. When mass is introduced, it physically forces the configuration slices to bunch closely together, driving the lapse function closer to zero. Because the lapse function determines the rate of experiential time, a value approaching zero mathematically requires that proper time passes slower in densely packed regions. This inverse proportionality maps directly to our macroscopic observations. The bunching of discrete slices is the exact, timeless mechanical origin of gravitational time dilation. Explaining time dilation is step one. The central theoretical challenge is mathematically proving exactly how this primordial discrete substratum transitions into the smooth continuum equations drafted by Einstein. To bridge that gap, we apply the functional renormalization group equation, or FRGE. The FRGE is a non-perturbative mathematical tool that interpolates between the bare, discrete behavior of quantum states and the effective macroscopic action observed at large scales. Within these duly weighted matrix models, the tensor size acts as the specific renormalization scale. This variable dictates the scale of observation by controlling the total number of degrees of freedom being calculated. As we scale up, we apply a coarse-graining procedure.
This involves grouping the discrete configuration vertices into specific clusters and mathematically averaging out their internal degrees of freedom. The mathematical target of this scale flow is a scale-invariant fixed point. At this specific boundary, the microscopic discrete fluctuations completely average out. Once the system hits this fixed point, the density of those discrete quantum states converges into the smooth line element of a Riemannian manifold. A Riemannian manifold is a curved mathematical space where distances and angles are smoothly measured at any point, identical to the spacetime of general relativity. The metric tensor of general relativity operates as a hydrodynamic order parameter, similar to fluid density fields in condensed matter systems. We can independently support this geometric derivation through the symmetric exclusion process, or SEP, calculated on random neighborhood graphs. The SEP provides a rigorous proof showing how discrete random walks of particles logically converge into continuous diffusion waves. This perfectly approximates the smooth differential operators heavily utilized in relativity. This statistical convergence from discrete walks to continuous operators provides the mathematical bridge to the Einstein field equations. General relativity emerges as the effective, long-wavelength fluid dynamic of a stabilized quantum spacetime phase. To address the quantum state, the VSD model relies on the many worlds interpretation. Under this, the universal wave function evolves unitarily and perpetually without ever collapsing. At macroscopic scales, interference between distinct states is suppressed through absolute decoherence. This natural dissociation forces the quantum state to split into a many spacetime structure populated by distinct classical 3D geometries. Physicists developed branching relativistic calculus, or BRC. This formal framework extends traditional tensor calculus, so it can accurately track vectors across a multidimensional branching architecture. Within this calculus is the multiverse metric tensor, a tool designed to generalize the description of spacetime and account for specific metric variations from one branch to another. This visual shows the modified Einstein field equation, integrating the branching stochastic variable. This specific term captures modifications to spacetime curvature triggered by time branches. As kinetic velocity increases, the required branching density scales sharply upward. This connects kinetic velocity directly to quantum branching. The faster an object moves, the more directional multiplicity it induces, driving the required forward branching density to higher and higher levels. The universal speed limit of light, c, represents the absolute physical saturation point of the substrate's capacity to calculate and render new branches. This diagram highlights the Ryu-Takayanagi formula, which synthesizes the profound connection between the emergence of macroscopic area and the underlying microscopic density of information. Based on this formula, geometric concepts like classical area and volume are merely emergent descriptors. What they are actually measuring is the density of short-range quantum entanglement between vertices. We can immediately apply this discrete density framework to regions of extreme gravity, directly addressing why general relativity breaks down mathematically at cosmic singularities. Because slice density is a literal integer count of discrete 3D configurations within a finite volume, it physically and mathematically cannot reach literal infinity. This limitation definitively regularizes singularities at the Planck scale. The Big Bang and black hole interiors are bottlenecks in configuration space, where the available branching multiplicity drops to its minimum possible value. In the eternalist VSD block universe, nothing actually happens or propagates forward in time. All geometries already exist in a fixed, static structure. Conscious observers are entities crawling up a pre-existing world line. We simply thread our way through a static 4D structural gradient, experiencing the passage of time strictly as the rate at which we process these geometric configuration updates. The perceived force of gravity and the forward march of time are both hydrodynamic illusions, emergent properties dictated by the density of a timeless, heavily branched quantum geometry.